Good day, and welcome to our webinar on troubleshooting techniques for AC induction motors, brought to you by CFE Media and Technology and sponsored by Allied Electronics, AEGIS, and Waco. Joining us today will be Michael Lita, Motor and Drive Engineer, and Ronnie Alford, Motor Lab Coordinator with Advanced Energy Corporation. I'm Kevin Parker, Editor of Plant Engineering Magazine. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported through RECEP at recep.net. A certificate of completion will be available for each participant to download upon successful completion of a test at the end of the presentations. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. To take the Learning Unit exam, use the Learning Unit Exam tab option at the top of the screen. The exam will open in a separate browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. Over their operating lives, most AC induction motors exhibit common problems, from transients to voltage imbalances and single phasing. Therefore, being familiar with general troubleshooting techniques is important. To start, it's vital to understand the operating parameters and forces acting against a motor, to perform tests and make observations based on those parameters, and to remove system components to isolate a problem. Proper size and power source connection must be verified. Regular measurement procedures, starting with nominal voltage, current, and frequency, can be the starting point for long-running optimal motor and drive operation. This webcast will specify and analyze the various troubleshooting techniques to consider and outline what equipment is needed to identify solutions. You see before you the learning objectives for today's session. To get the best results from the webcast platform, please make note of the following. For technical problems, click on the question mark at the top right-hand corner of the screen to bring up a list of system checks to make before escalating to an online technician. If you experience issues with the slides or audio, please refresh the browser or click the Refresh Media button directly under the presenter's headshot. Volume settings can be controlled by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If a technician is needed, type a message into the Ask a Question box and someone will get to you as quickly as possible. Answers to technical questions will be in the Answered Questions box on the left-hand side of the screen. The Ask a Question box is also used to ask the speakers questions. Ask questions at any time during the presentation. We'll get to as many as time allows. To download the presentation slides and certificate of completion, use the Event Resources box on the left-hand side of the screen. You can download the presentation and certificate of completion until the conclusion of the webcast. The link will break when the webcast signs off. This webcast is being recorded, including the Q&A session. We'll send you an email message within a week with a direct link to the webcast archive. We'll now hear from the sponsors of today's webinar. At the end of the videos, you may experience a few seconds of silence to compensate for varied internet speeds. Stay tuned for today's presentation and discussion.
Allied Electronics and Automation has plans. Big plans. As one of the country's top suppliers of automation and industrial parts, they aspire to be a multi-billion-dollar company. They'll get there by offering a breadth of leading solutions that's unrivaled in the industry, by providing world-class service for a growing base of customers, and by investing in the future with a state-of-the-art fulfillment center. The advanced automation in Allied's newly expanded distribution center doesn't just help them deliver products faster. It helps them deliver value-added services that save customers time and money in the procurement of products.
VFDs can save 30% or more in energy costs. but VFDs can damage motor bearings. Without shaft grounding, VFD-induced voltages can discharge through motor bearings, causing damage such as pitting, frosting, and fluting, and unplanned motor failure in as little as 3 months. Aegis shaft grounding rings provide proven long-term protection against VFD-induced bearing damage. By channeling harmful shaft currents away from bearings and safely to ground, Aegis rings ensure that motors last for the full L10 life of their bearings. And while you can install Aegis rings yourself or have a motor repair shop install them, the easiest way to protect your motors is to purchase them with Aegis rings factory installed from any of a growing number of motor manufacturers. To protect VFD motors, always specify Aegis rings. To learn more, visit the Aegis website and schedule a lunch and learn worth 1 hour of professional development.
Welcome to WAGO's North American headquarters located in Germantown, Wisconsin. As the innovators of cage clamp, WAGO has been the world leader for over half a century in the design and manufacture of termination systems incorporating spring pressure connection technology. We have been changing industry with our innovative products since our founding in 1951. Today, our company offers a full range of products including electrical interconnect such as rail mount and PCB terminal blocks, electronic interfaces like power supplies and signal conditioners, and automation products including I/O systems and touch panels to serve a multitude of industries including manufacturing, lighting, process, and more.
Welcome back. I'd now like to introduce today's speakers. Ronnie Alford joined Advanced Energy in November 2018, having spent the past 2 decades with the Electrical Equipment Company. Ronnie conducts motor systems testing, implements lab improvements, maintains calibration certifications, and conducts training. Ronnie received his associate degree in HVAC and refrigeration engineering technology from Wake Technical College in 2001. Ronnie is also an approved auditor for the EASA accreditation program for third-party quality motor repair. Michael Lita started working for Advanced Energy Motor Lab in January 2010 as a co-op student. He moved into the laboratory director role in August of 2019. Michael is involved in motor systems testing development, research, and training for a wide range of applications. He received his bachelor's degree in electrical and computer engineering and minor in mathematics from North Carolina State University. Michael is also a member of the Advanced Energy Commercial and Industrial team, participating in energy assessments and recommending energy conservation measures at regional facilities. Michael, welcome to today's webinar, and please go ahead.
Thanks, Kevin. Thanks for that introduction. On behalf of Ronnie and myself, I would like to thank Kevin and Emily and the CFE media team for giving us the opportunity to present today. I want to start with a brief background and description of Advanced Energy, and then we'll watch a short video and then get into the material. Advanced Energy was founded in 1980 by the North Carolina Utilities Commission to investigate and implement new technologies for distributed generation, load management, conservation, and energy efficiency. We are an independent nonprofit corporation governed by a board of directors. That board of directors is appointed by the governor of North Carolina and our member utilities. We continue to work with those member utilities on energy efficiency and conservation projects still today. Our current North Carolina member utilities include Duke Energy, Dominion North Carolina Power, and North Carolina Electric Membership Corporation. In addition to creating means for sustainable, energy efficient economic development for the ratepayers of our state here in North Carolina, We also operate as a fee-for-service consultant to clients nationally and internationally. We work with electric utilities, government, and then a wide variety of private organizations in 5 targeted areas, which include residential, commercial, industrial, solar, motors and drives, and electric vehicles. Our customized services include research, testing, training, consulting, and program design. Ronnie and I both work on the motors and drives team here at Advanced Energy, and we do want to show a short video. I promise this is the last one. It's going to describe a little bit about our team and what we do. It'll take about 2 minutes.
Motor-driven systems are estimated to account for approximately 50% of all electricity generated in the world. This fact is what first attracted Advanced Energy to motors in the late 1980s, and why we continue to work diligently today to make motor-driven systems as energy efficient and reliable as possible. Our team of motor and drive system engineers, combined with our internationally accredited test lab, provides a unique set of independent and unbiased services to governments, original equipment manufacturers, motor and drive manufacturers, utilities, distributors, and motor repair facilities. Testing motors and drives is the foundation of our programs and services. In 1997, we became the first motor lab in the world to be accredited for motor efficiency testing by the National Institute of Standards and Technology under the National Voluntary Laboratory Accreditation Program. Our lab is designated for AHRI 1210 certification for variable frequency drives. We are also the first lab outside of Mexico to be designated for non-motor efficiency testing to meet Mexican requirements. Our lab is accredited to ISO 17025, and we use these operating procedures to train all of our employees, providing confidence in our results and our independence as a test lab. Advanced Energy is also recognized by ANSI as a certification body to ISO 17065 for energy efficiency verification services, including small electric motors, and generators. We are committed to quality testing that results in accuracy and repeatability. We are continuously expanding our testing services and capabilities to help clients meet new demands and challenges. From product development testing and motor design services to performance and endurance testing, we are your trusted partner for customized testing of motors and drives. We believe that motors and drives are incredibly important, and we find it exciting that we can make a difference by ensuring that they are reliable and energy efficient.
All right, so let's get into the meat of our presentation. So today we'll mainly talk about alternating current or AC induction motors, although a lot of the techniques we're going to discuss would apply to other, different motor types as well. Our presentation is going to be divided into 4 sections. So I'll start by covering some basics and then causes of failure, and followed by forces acting against the motor. And then Ronnie's going to take over and cover test methods and equipment that can be used, and then diagnosing symptoms and solving problems, including various real-world examples along the way. So first, I'd like to get started by going over a few of the basic components found in an induction motor. So you'll hear many of these components referenced throughout the slides. The rotating components are labeled on this picture. The shaft is on the left, which is where the motor would couple to the load. The rotor, which is painted red in the picture. Then the rotor paddles and the balancing nubs, which are shown in cast aluminum. That's labeled number 3. And then labeled number 4 would be the shaft fan, which for this motor you can see is plastic. The side of the motor with the shaft side, which is where you'll couple to the load, that would be called the drive end. And then the other side, of course, just named the non-drive end or opposite drive end. Keep it pretty straightforward. So some housing components are shown here. End bells are on both sides of the motor. The bearing housings and the stator housing in the picture are painted the light orange color. The cooling fins are on the outside case of the motor. And then it's hard to see, but there's a junction box where you will find the terminals. That's labeled number 8. And then finally, number 9 would be the fan shroud, which will be used to safely guard the fan during motor operation. So we have the fixed components on this third slide. It's going to be shaft seals, stator windings. It's kind of, I'm not sure how big it is on the screen, but stator laminations is number 12, and then bearings. So you have bearings on both the drive end and non-drive end, one bearing on each side in most cases. The bearings, of course, will be the most influential component on motor life, and we'll talk about that here in the next slide. So we're going to talk about causes of failure. Electric motors are, of course, electromechanical devices which have the electrical and mechanical components. So we're going to talk about electrical and mechanical failures. The bearings, if you can see on the right side of the screen, those will be the leading cause of failure. So this is a study, a chart taken from the Institute of Electrical and Electronics Engineers website, IEEE, and it lists over 50% of motor failures stem from bearing issues. So some examples of bearing issues might be lack of lubrication, lack of greasing, incorrect lubricant, even over-greasing, misalignment, parallel angular misalignment to the load, or causing vibration, excessive vibration, and overloading or overheating. Down in the orange part of the pie chart will be the second leading failure type, characterized as stator winding failure. Here, we're thinking short circuit faults, line to ground faults, or maybe even a few cases open circuit fault. You may notice on the chart, external or environmental conditions are a leading cause of failure, and we'll get into that deeper here in a few minutes. You also may notice that overheating and overloading are common to many of the failure types listed. And it's very important, not to be overheating, motor not to be overheating. That definitely leads to premature failure. And it's also important to understand the application to avoid the overloading issue. Overloading for increased periods of time will definitely lead to overheating of the motor itself. So when you match a motor to an application, it will typically be matched based on nameplate speed and horsepower, target output. In many applications, the motor may experience short-term overloads, and due to this, most motors would be marked with a service factor. So the service factor could be found on the motor nameplate or in the product literature. Most motors would be equipped with a service factor greater than 1.0, which means they could safely operate above rated load for short periods of time. So definitely keep in mind, limiting failures, premature failures. Verify your nameplate service factor if you suspect some overload may be occurring. Next, we're going to take a look at the various forces acting against a motor during operation. For a motor to perform within design specifications, the running temperature must be kept at or below the insulation class rating. The applied voltage should be well balanced and as close to nameplate rating as possible. The starting torque and the rated torque need to meet the load requirements of that application. And then the mechanical friction within the motor needs to be able to be overcome during startup. Heat is typically going to be the primary source, primary damage to motor components. Excessive heat can occur from things like, elevated ambient temperature, unbalanced voltage at the mains, blocked or limited fan cooling if the motor does have a fan, and then of course overload. And we already talked about vibration from parallel angular shaft misalignment. And then even heating from if the motor isn't correctly sized or the correct motor for the application itself. When we do talk about heat and motor temperature, you may wonder what the operating temperature is appropriate for a specific motor. So the National Electric Manufacturers Association, or NEMA, as well as the International Electrotechnical Commission, or IEC, they have standardized operating temperatures. So these, as already stated, are defined as insulation classes. Motors are going to be rated with an insulation class which applies to the insulation on the windings, the electrical wires inside the motor. But the bearings and other components would also be rated at temperatures above that insulation class rating. So looking at the NEMA rating specifically, since I think most of the case here we're in America, the higher the letter, the hotter the motor can get. So in other words, a Class H insulation you will see is rated to run at a higher temperature than a Class F insulation. So definitely always also pay attention to the motor's rated ambient temperature. Most motors these days will come standard to operate in a 40 degrees Celsius ambient, and if that is the case, it should say so on the motor nameplate. Also keep in mind that even though you may have a motor with, for instance, Class F rating, that doesn't mean you would expect the motor to operate at the temperature here on the chart, 155 degrees C. Most motors will and should run much cooler than what their class rating is. And then a general rule of thumb in the industry is for every 10 degrees Celsius of higher run temperature, your motor winding life would be cut in half. Of course, this is just a very general rule of thumb, also dependent on ambient temperature and various other environmental conditions as well. Along with temperature, the voltage is the second force acting on the motor we're going to talk about. Always verify the rated voltage on the motor nameplate. Sometimes you may have multiple voltages on the motor nameplate. A few years ago, we had a failure. We reviewed a failure, and it was a dual voltage rated motor, which is very common. The motor was connected to a 40 volt supply, but it was wired on the terminal side for 240 volt operation. So the motor actually did, operated for a little bit of time, but once the failure occurred, it was very ugly, and the motor couldn't be rewound. The core was damaged beyond repair. So definitely pay attention to, what the wiring is, and then also what your incoming voltage source would be. So one other thing I wanted to point out is most low voltage motors typically would be rated at like 460 volts. But grid voltage coming from your electric utility might typically be 480 volt. So the 460 volt rating takes into account voltage drop in the distribution lines coming from the nearest substation or nearest distribution transformer. We have actually completed some tests at our lab here in Raleigh that shows a slight increase in supply voltage above the rated voltage will actually lead to increased motor efficiency. So that test showed that multiple 460 volt rated machines operated most efficiently at approximately 1.05 per unit voltage, roughly 480 to 485 volts. That same testing also showed that lower voltages than rated are very detrimental to motor efficiency. And according to the Electrical Apparatus Service Association's Electrical Engineering Handbook, if you look at a approximate 10% voltage drop, the motor design torque would be reduced by approximately 20%. So, in general, if the lower voltage is supplied to the motor will need to draw more current to output the necessary torque and speed for the application. And of course, higher torque, higher current draw will lead to overheating, and then we already discussed the overheating is a major cause of the premature failure. So continuing to look at the voltage imbalance is another major problem. So we've had, quite a few metering and verification projects over the years. We've seen large amounts of voltage imbalance at the field facilities, just like yours. We do work with the utilities very often, and the utility will typically have a power purchase agreement in place with your facility, and it will set a limit on the amount of voltage imbalance that would be coming from the grid side. Typically, those PPAs will be set somewhere in the 2 to 3% voltage imbalance range. So, generally 2 to 3%, that doesn't seem like much, but 2 to 3% voltage imbalance can be detrimental to motor population, motor efficiency, motor population over time. So, the point that I want to make here is that even the minor voltage imbalance can lead to horsepower derating for the motor. You will see this chart here on the left side shown from National Electric Manufacturer Association, NEMA's Motors and Generators 1, which I call the Motor Bible. It shows the voltage imbalance when exceeding even 1% can lead to derating and excessive heat. So keep in mind the voltage imbalance directly leads to current imbalance also. So industry rule of thumb is that for every 1% voltage imbalance, a motor could show a 7 to 8% current imbalance. The high current imbalance is detrimental to motor operating conditions, and the higher currents on an individual phase can lead to hot spots in the motor windings and early failure. But of course, voltage imbalance isn't the only thing that can cause some current imbalance. Unbalanced winding resistance could lead to it also. If you're measuring current imbalance with an ammeter, out in the plant, if you have your motor loaded or unloaded, you're seeing some current imbalance, de-energize your motor and then measure each phase-to-phase winding resistance so you can verify kind of what that baseline resistance imbalance is. So moving on from voltage, the third force acting on the motor that we'll look at is torque. Some initial considerations include, does the motor design type match the starting and rated torque requirements of the application? Does the load vary over time? And could the load exceed rated torque requirements at any point? And then finally, are the effects of heat derating motor performance? So similar to insulation class rating, NEMA and IEC have standardized how we reference the starting current, the torque design, and the speed or the slip of electric motors. So there are many different NEMA and IEC design codes. We're only going to go over the most common in this case. So NEMA Design B and equivalently IEC Design N are the most commonly used motors in the industry, and they would be referred to as current limited, low slip, general purpose motors. So NEMA Design A would be similar to NEMA Design B, but they don't have that starting current limitation like NEMA Design B does. NEMA Design C and equivalently IEC Design H motors would be moderate slip, high torque motors, but with no starting current limitation. With the current limitation. And then NEMA Design D would be just like Design C, but without that starting current limitation. So NEMA Design A and B motors would be popular for like typically centrifugal applications like blowers, fans, pumps, general industry, process use. And then NEMA Design C and D motors would be better suited for high starting torque applications like elevator, crusher, conveyor, air compressor. It's worth noting NEMA Design D is the only one of those 4 standard design types that isn't currently regulated by the Department of Energy to motor efficiency requirements. So NEMA designs A, B, and C are regulated and must list the nominal efficiency along with the certificate of compliance number on the motor nameplate. The fourth and final force acting against the motor that we're going to cover here is the mechanical friction. So mechanical friction is directly dependent on the motor bearings. A good place to start is with the motor alignment to the load. So a parallel or angular misalignment can lead to many problems over time, but it's especially critical to controlling the vibration and mechanical wear. So all manufacturing tolerances must be met. And some key tolerances include the rotor balancing, the shaft run out, the bearing housing, and bearing fit. Also, it seems straightforward, but correct bearings must be used for the application. Just to give an example, standard ball bearings will be used for direct coupled load or lower torque belted load. But a roller bearing would typically be used for belted applications with a higher, radial load. And then if you think about vertical motors, consider whether you have some axial force, if it's upward, downward, or balanced force to determine if you need the thrust bearing on one end of the motor. Most commonly matched also with a guide bearing on the opposite end. And, just to reiterate, we did talk a lot about bearings. The bearings are the number one cause of motor failure, so it's very important to follow your preventative maintenance techniques with your bearings, periodic lubrication, vibration analysis. Even when you're greasing the bearings, you got to verify you're using the right grease. These days, I think Polyrex EM is the most common recommended grease type. And also, if you need to measure that grease, measure it. Find some way to weigh the grease before you put it in. The bearings should be maintained based on run hours, and product literature from the bearing manufacturer should give specific details on the lubrication type, the interval, and the amount to add. So that covers the causes of motor failure and the forces acting against the motor. I'm now going to turn the presentation over to Mr. Ronnie Alford, who's going to walk us through the problems to look for when troubleshooting and which tools to use. Take it away, Ronnie.
All right, thanks, Mike, and thank you to everyone for allowing me to present today. So let's take a look at what problems we may encounter when troubleshooting motors and what tools we may use in the process. One key factor that plays a part in troubleshooting motors is knowing the motor data and the motor's history. When we talk about motor history, we're talking about how long the motor has been in service and how many run hours the motor encountered. When troubleshooting motors, if you think a motor failed prematurely, then not only do we want to look at the in-service time, but it's also a good idea to know how long the motor was out of service before running. This meaning, was the motor a spare that had been sitting on a shelf for a period of time before it was installed, or does the system have multiple motors that are used for the same process? There are many cases where motors will sit for months where there is no controlled environment, maybe in storage, and the motor shaft is never rotated. This can lead to many premature failures, such as flat spots on the bearings or moisture buildup on the windings of the motor, therefore making this an important part of the troubleshooting process. When talking about motor data, we also want to confirm that the motor in service is appropriate for the application by verifying its mechanical and electrical characteristics are correct. We can accomplish this by first collecting data from the motor's nameplate. Here I have given an example of a few nameplates that you would see on a typical AC induction motor. As you can see, there is a lot of information and many different details that can be used during troubleshooting if we understand exactly what we're looking at. So let's take a look at a few of the items on the motor nameplate and what they mean. First, we will see that there is a specific model and serial number tied to each motor. This information can be very helpful when you get to the point of having to replace the motor and you want to make sure the new motor has the same characteristics as the previous motor in service. But with that being said, when ordering a new motor, we also want to make sure it's the correct motor for the application. So make sure that the application information is also passed along to your motor supplier. I've seen many times in the past where a motor matched the basic nameplate data such as horsepower, RPM, and volts, and therefore was put in the place of a motor that was built for a specific application. A good example would be a kiln duty motor that can withstand higher temperatures, or a washdown duty motor that can withstand direct water contact. There are many motors built for specific applications and therefore make it just as important as the motor nameplate information itself. Next, you will see the output rating, which is listed here as HP for horsepower or kW for kilowatts. You will see the speed, which is normally notated as RPM, simply meaning revolutions per minute. And the speed and output power are both always important when troubleshooting a problem, or if you're just simply looking to calculate the torque value of the motor. Lastly, here we see that the voltage is always an important item to document to make sure the proper line voltage has been applied to the motor. Many motors will give you the option of wiring the motor for different line voltages. Yes, we'll see such as 460 volt, 230 volt, or even 208 volt. So it is always important to check that the motor has been connected for the proper line voltage rating. The current rating can play a big role when troubleshooting a motor. That may be given you specific faults to current draw issues. And of course, the current can be notated on the nameplate in a few different ways. FLA is the most popular abbreviation, which stands for full load amps, meaning current draw at rated horsepower at a given line voltage. All right, if your motor is on an application where the torque fluctuates, it is always a good idea to have a motor with a higher service factor. This will allow the motor to withstand a short period of time where the motor can be overloaded by the service factor multiplier. This meaning if the motor has a service factor of 1.25, the motor can run at 125% of rated load, while keeping in mind that overloading factors lead to higher currents, which in turn leads to higher motor temperatures. Always monitor the motor temperature closely to eliminate any chance of shortening the life of the motor. As Mike talked about earlier, the insulation class indicates maximum allowed internal temperature a motor should operate, and these classes are based on a motor designed to operate at a 40 degrees C ambient temperature. So standard class rating for a general purpose NEMA motor is usually referenced as class F, but if you know your application is withstanding ambient temperatures above 40 degrees C on a regular basis and the motor runs at full load most of the time, it's best to order a motor with a higher class, such as class H insulation. Just knowing that heat is the leading source of motor failures, it is always best to make sure that the proper ventilation and temperature monitoring is always in place. All right, making sure you have the correct enclosures. Lastly, here can play a key part in cooling for the motor. There are many different types of enclosures, such as TEFC, meaning totally enclosed fan cool, ODP, meaning open drip proof, TEAO, meaning totally enclosed air over, as well as many others. Each motor enclosure can be specific to an application and to the environment the motor is located in. Now that we know how to compile the data from the nameplate, we need to troubleshoot or replace our motor. Let's look at a few steps to take when moving forward with looking for problems that are occurring with our AC motor application. I always like to include the importance of safety and how it should always be the first priority of troubleshooting, not only in AC induction motors, but on any piece of rotating apparatus in a facility. When troubleshooting a motor that you're going to have to physically touch any part of the motor application or have to remove any safety guards to troubleshoot, please make sure that proper PPE and lockout tagout procedures are followed. It's also a good idea to advise all appropriate personnel of the inspection. You do not want anyone to be aware of what is going on and accidentally put your safety in jeopardy by starting a piece of equipment. Because at the end of the day, our main goal is to be able to go home to our family without any injuries. Now that the first key step has taken place and all proper procedures have been followed, we can move into looking at a few basic mechanical inspections. When performing any kind of troubleshooting, do not get ahead of yourself in the thinking process. I'd say always look for the obvious signs first. Some simple but important things to look for when performing a mechanical inspection we have listed here would be such as looking for hot spots on the motor frame, meaning discoloration of the paint. If a motor has withstood enough heat to show signs of external hot spot, it gives us a good idea of the degradation of the components and winding inside the motor I've seen. We would look for leaking lubricants under and around the motor. Leaking lubricants can play a big role in understanding if the motor bearing grease is getting too hot or if the motor bearings are not getting enough lubricant due to the leak. We see broken or missing parts. As always, an easy but effective inspection. Broken or missing external fan blades can play a vital part of troubleshooting a motor with accelerated temperatures or even high vibration due to unbalance. We could look inside the J-box, terminal box, for any signs of arcing or contaminants, just as we see here in the picture. And as we touched on earlier about motor enclosures, it is always good practice to look for blocked airflow paths. For example, on a totally enclosed fan-cooled motor, there are a lot of applications that can cause the fan cover vents to get blocked from the materials in the environment. For example, damp paper or sawdust particles, rock dust, or even metal slag, just depending on your process and plant. There are so many different contaminants that can produce cooling problems, but sometimes there's just basic human error as well of leaving a box too close to the motor or adding components to a motor to help with contamination buildup, but then not allowing enough room for air to flow properly through the motor. Once the basic visual inspection has been performed, move on to check for rotation of the shaft by hand. Is the machine free to rotate? If you cannot rotate the motor shaft when coupled to the driven machine, uncouple the motor and check for free rotation of the motor shaft, and just listen for any noise coming from the rotating parts. A lot of times it's easy to hear or even feel a bad bearing or rotor dragging inside the stator. But in some cases, you're suspecting a mechanical issue before it becomes a failure because you notice high vibration coming from the motor, but not very clear on where the source is coming from. In this case, you'd want to extend your options and perform vibration analysis. Vibration analysis is the most common mechanical test for preventive or predictive maintenance. This test is performed by using an FFT spectrum analyzer and using an accelerometer that is usually placed in the horizontal and vertical planes of both bearings and actually on at least one of the bearing housings. There are standards that apply to the acceptable limits of vibration, but may note that the standards such as NEMA state the acceptable limits apply only to uncoupled motors, where most of the time we're starting our analysis with the motor coupled to the driven machine. NEMA acceptable limit is 0.15 inches per second peak for resilient mount motors and 0.12 inches per second peak for rigid mount motors. And to help clarify that limit, the limit's higher for a resilient motor due to the movement that is allowed by the rubber or other types of isolators used during mounting. This is normally seen in smaller motors such as on a fan or blower application. And I recommend always taking vibration readings of the motor coupled to the driven equipment first. That way you can help eliminate and pick up on any signs of misalignment or coupling wear or even unbalance of your driven equipment. All right, now that we've looked at a few different types of mechanical test methods and troubleshooting, let's take a look at a few things to focus on during the electrical inspection portion of troubleshooting AC motors. Just as in any portion of the troubleshooting process, start with the basic task and work your way to the more in-depth testing processes. First, we should know that it is best for these tests to be performed by someone, of course, that has been trained in electrical testing. By using a voltmeter, we will first check for applied line voltage at the power supply of the motor at each line to ground to eliminate any potential blown fuses, and then we can proceed to test each phase line to line. The applied voltage could be direct wired from a simple on-off switch, or it could be coming from somewhere a little more complex, such as a VFD or a soft starter. When performing these tests from a control circuit, such as a VFD, we will want to make sure that the power is available at the incoming and outgoing side of the unit when in run mode. Another useful test to perform when troubleshooting a motor with an electrical fault is the ground wall and continuity test. And I would make sure, if your motor is powered by a VFD or soft starter, that you disconnect the motor leads from them before beginning these tests. The continuity test can be performed with an ohm meter and should be tested from the leads coming directly from the start switch or VFD. By doing this, you can eliminate any possible broken power cables that are running in conduit or underground. If the continuity test fails, disconnect the incoming power cable at the motor terminals themselves and perform the test again between each phase of the motor. That way you can pinpoint if the failure is in the motor or in the power cables. If no cause of failure has been determined at this time, we can move on to performing an insulation resistance test that checks for any ground faults in the ground wall insulation. This test can be performed by using a megohm meter, also known in the industry as a megger. You will see in the upcoming exercise how this test can be beneficial. All right, I know this slide is very busy, but we will work through it together. Here we are looking at an example of a 460 volt AC induction motor that will not start. Once we go through the preliminary test that we covered earlier on testing for supply voltage at all three phases and eliminate any blown fuses, we move to the next system component. The control circuit is tested to make sure proper supply voltage is coming out of the unit. If a fault is coming from the VFD or soft starter, use the code given to help troubleshoot the problem. If a grounded motor is suspect, then this can be tested by performing the insulation resistant test, or also known as an IR test. With this test, the megger or megohm meter applies 500 volts DC to the motor and measures the resistance of the insulation to ground. The applied DC voltage is why it's important to remove the motor leads from any control circuit that may be used. The recommended minimum insulation resistance value at 40 degrees C for most motors with random wound stator coils is with DC voltage applied for 1 minute is 5 megohms. And that can be found in IEEE 43 standard. Load readings may indicate reduced insulation conditions caused by contamination or deterioration from excessive heat. But if the motor tests at 0 megohms, the motor winding circuit is grounded and the motor will need to be repaired or replaced. Please note that a megohm meter cannot determine if a complete motor winding circuit is good, as well as determine turn-to-turn or phase-to-phase faults. These tests will need to be performed by more advanced motor circuit testers. So we have learned from all the considerations that we have looked at today to perform tests and make observations, understand the operating parameters, and remove system components until you isolate the problem. You'll see here that I've listed a few of the standards that that we have referenced today throughout the presentation, along with a few additionals. The IEEE 112 standard for test procedure of polyphase induction motors and generators, the NEMA MG1 standard for motor and generators, and the ESA AR100 standard for recommended practice for the repair of rotating electrical apparatus. And they're all great references to use when troubleshooting AC induction motors and are looking for specific guidelines. On behalf of Advanced Energy, Michael and myself, we would again like to thank you for allowing us to present this topic to you today. And at this time, I will pass it over to Kevin for our Q&A session.
Well, thanks so much, Ronnie. And we've got a considerable number of questions already, so let's get to it. Just for our audience to know, the questions that we don't get to will be archived along with the archive version of this webcast, and it will be documented in the pages of Plant Engineering in coming months as well. Let's go quick to some questions. Ronnie, where is the best place to start to implement a predictive motor maintenance program?
Thanks, Kevin. That's a great question. I would say the best place to start a predictive maintenance program within your plan is with your most critical applications. Now, I would consider those the heart of your plant, or process. And then once you have your critical equipment on a regular routine program, you can extend into the rest of your equipment. Just to add that there are also software programs that can assist with your programs as well, to start off and just being able to maintain and keep record for you during that process.
Thanks, Ronnie. Michael, what type of damage can VFDs cause on motors?
Yeah, very good question there. A lot of people talk about the benefits of adding a variable frequency drive onto a motor, and you will find less talk about some issues with adding VFDs onto motors. But because the VFD it's not a perfect sine wave, right? You're passing a kind of a square wave, a pulse width modulated signal to the motor. You're going to see some pretty severe peak voltages at the motor windings. You're going to see some, very quick rise times. Inverter duty motors, which will typically be, or inverter rated motors, some question in the industry about those two definitions. Those will have, VFD rated cables that go up to a higher voltage. Most of your low voltage motors will have up to 600 volt, winding cables. You will have higher voltage ratings. We saw we're not endorsing any products here, but we did see the advertisement for the Aegis grounding rings. The shaft grounding is a big thing with motors that utilize VFDs, because the bearings, if shaft's not grounded, can take some damage, and it will cause fluting and blackening of the grease, and all of these things can lead to premature failures.
Well, thanks, Michael. Ronnie, a question for you. What are the best practices for motor greasing intervals?
Yes, another good question. I would say that this will depend on the run hours of the motor, and that also the speed of the motor and the type of grease being used can all play a key factor. But just remember that a big part is the run hours of the motor, not just to necessarily grease all your motors at the same time on a schedule. It's not unusual at all for different motors in your plant to be on different greasing intervals due to the run hours or the speed of the motor. But you can reach out to your grease supplier for greasing charts for the specific type of grease that you are using, and the speed of the motor will kind of allow you to know how much grease to add in a specific interval period.
Thanks, Ronnie. Michael, for the installation temperature ratings, where exactly within the motor is the temperature reference?
Yeah, that's going to be on the stator windings. So, where the current's flowing through the windings, through the motor terminals, that's going to be the hottest part of the motor. So, that's the installation class rating would be referring to the stator windings.
Thank you. Ronnie, how does one properly use a megger?
Okay, on that question, a megger is a specific brand name for an insulation resistance tester. So there is a standard that's in place, that's the IEEE 43 standard, that's put in place to allow you to know how much DC voltage to apply to the winding, depending on the rated winding voltage. And there are a few different steps that an insulation resistant tester can take. And then also to follow up on what is the recommended minimum insulation resistance value. So kind of as we went through our example earlier, a winding that's rated for less than 1,000 volts, or say a 460 volt winding, you would apply that 500 volt DC, and you're expecting to see a IR minimum at a 1 minute test of 5 megohms. And that standard's for most machines with random wound stator coils and some form coils that are rated below 1,000 volts.
Thank you, Ronnie. Michael, let me ask you a question. When is it all right to overload a motor?
Yeah, so it really depends. We did talk about the service factor. In induction motor, you're going to be able to get a high amount of torque out of these things for short periods of time. And so we showed the curves, the NEMA design curves. You've got the breakdown, basically. Breakdown, we're talking about 250% rating sometimes. If you run the motor any above its rated load for long periods of time, it's going to cut down on motor life. We talked about some general rules of thumb. We could be talking about limiting motor life from 20 years to 15 years. So it's all relative. But short-term short-term overloads, look at your service factor. You can't really measure out in the field. There's limited equipment to measure torque, or output. You can measure speed with a tachometer. You're most of the time checking your current on the input side, electrical side, with an ammeter. So compare your current on the input side to the rated current on the machine. If you're staying below that, typically, you're running below the rated output.
Good. Another question. If a motor is coupled with the magnetic center offset, would you expect a bearing heating issue, or what would be the most expected indication of the alignment issue? Is this a larger issue with vertical motors versus a horizontal mounted unit? And that's for either or two of you.
Yeah, I can start. I could start on that one. I think you will be listening for audible noise issue. Expect some. If there is a misalignment, you hear some audible noise. You can use the vibration analyzer if you have one to verify that. I'm not really sure on a larger issue with vertical versus horizontal.
Okay.
Well, thanks for taking it. Ronnie, did you want to take a swipe at that one?
Yeah, I'm not sure I understood the whole question, but I know there was some reference in there of magnetic centering. When we're talking magnetic centering, most of the time you're talking about like sleeve bearing motors. So it's always a good idea to energize that motor and run the motor before even coupling it to the driven application, so that you can scribe the shaft of where the magnetic center falls. Therefore, when you do have it coupled up, that you're not forcing against the bearings of your driven equipment and damaging those bearings.
Good. Well, I'm afraid that's all the time we have for questions today. We tried to get as many in as we could, but as I say, we're going to follow up on the website and in the magazine. I'd like to thank Michael and Ronnie for participating in today's event, and I'd like to thank our listeners for attending as well. We hope it suited your purposes. I'd like to thank our sponsors for today's webcast, and now that we're just about done, we'd like to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it as we use this information to improve our webcast. On behalf of CFE Media and Technology, we look forward to seeing you next time.